So, good morning. Welcome to Krishna's classroom. Continue with our Lebesgue integration theory. And last time we were working on the characterization of Riemann integrable functions in terms of the Lebesgue measure and Lebesgue integration. We were trying to work that out. And then we stated the theorem. And we proved one part of the result, namely, we proved that if AB is R properly continuous, or it's a compact, bounded, and if F is bounded on real value on AB, these are the basic conditions that we then F is Riemann integrable you know that not necessarily all bounded functions are Riemann integrable. Okay. Then F is Riemann integrable if F is continuous almost everywhere on, this is what we proved last time. So the assumptions were that AB is a bounded interval, F is a real valued function which is bounded, and then of course it satisfies the preconditions for Riemann integrability. Then we proved that F is Riemann integrable if F is continuous almost everywhere on AB. That means the set of discontinuities of F on AB is a set of measure 0, right? So that's a condition. That condition is satisfied, then F is Riemann integrable. Now, we prove the converse. So what is the converse? The converse is that if F is continuous almost everywhere on AB, that is, we prove if F is continuous almost everywhere on AB, then F is Riemann integrable. This is what we want to do. This is the part that we are going to do. That would complete the characterization. So together, then it would mean that f is Riemann integrable if and only if the set of discontinuities of f is a set of measure 0. So together, then f is Riemann integrable if and only if the set of discontinuities of f is a last time I gave in fact, I think we have nearly proved this actually while considering the Riemann integration, but in a totally different language. And what we said was that if the set of discontinuities form a null set, which we had defined at that time, then it is of measure, then it is Riemann integrable and vice versa. So the concept of null sets there, because we had not introduced the concept of measure at that time. So it's only later that we introduce the concept of Lebesgue measure. And therefore, what turns out to be is that what we call a null set is essentially set of measure 0. Okay, so just keep that in mind. So let us now, with this introduction, now we assume f is Riemann, f is continuous at almost all points AB. Then what we claim is that now this is what we prove. Okay, right. So how do we prove this? Okay, so this is the statement that we are attempting to prove. So let us prepare the ground. We want f to be Riemann integrable. Now you see that the Riemann integral of f is essentially, or Riemann integrability is essentially the equality of the upper integral and lower integral. Or another way of putting this is that you take the difference between what is called the upper sum and the lower sum, okay, over some partition of this, and then push the interval length to 0, then this difference should go to 0. That is a necessary and sufficient condition for Riemann integrability. So we will verify that. So let me do that. So let Pn be any sequence of partitions of the interval AB such that the interval length actually goes to 0. That's the point. Okay. That means you refine, and so on, and go to the limit of this. So this is what I am saying. So what you have is this, such that the limit n tending to infinity of gap of Pn equal to 0, where gap of Pn is the maximum of interval length in the partition En. What does it mean? It means the following. Suppose, let me write, suppose Pn is given by, say, A equal to x naught less than x1 be a partition of the interval AB. Okay. Now, what you call gap of Pn is essentially the maximum over I of I minus 1. Okay. Right? This is the gap. So what we mean to say is that the maximum width that you have for this partition is what you write as this. And we make that go to 0, which means that the partition becomes very refined. That's what. Okay. Then we have f Riemann integrable over AB if and only if limit n tending to infinity of upper sum lower sum of Pn. Please go to the definitions of U and L related to the Riemann integration, and this is equal to 0. So this is the condition. This is a necessary and sufficient condition for F Riemann integral. We will work on that. Okay. So let's do this. So our effort will be to prove this. But in this context, we'll make use of the boundedness convergence theorem or bounded convergence theorem. Let us see how we do this. Then you would have the following. This is, suppose, assume this is true. Then this is the proof of this actually. You have 0 less than or equal to integral a to b, that is the upper integral of f minus the lower integral of f, which is less than or equal to u and what you are proving is that this goes to 0. So this goes to 0. And once this goes to 0, what happens? These two integrals, the upper integral and the lower integral of f, will get squeezed between 0 and 0. That means equal to 0. Have equal to 0. So we have worked out the strategy for proving this. Okay. So what did we assume? We assumed that f is continuous almost everywhere on AB. That is only on a set of measure 0. Possibly it is not continuous. If so, then we prove that f is Riemann integrable, and this is the strategy. Okay, so let us elaborate on this. Now for each n, what you have is that be the lower and upper step functions associated with because you know that essentially this would facilitate, we are trying to facilitate an approximation from below by phi n and from above by a function psi n, and then what you have is that your f gets squeezed between this upper approximation psi n and the lower approximation phi n. And then this amounts to actually showing that limit n tending to infinity psi n minus phi n goes to 0. Okay. You see, this one is essentially, then we have essentially integral of a to b. This is the upper integral, so this is psi n minus integral a to b phi n. So what you want is, this is essentially you are looking at integral a to b psi n minus phi n. So what is that you have to prove? You have to prove that this integral goes to 0. This is what we do. That is, we prove that limit n tending to infinity zero. So this is proved in terms of this now. Okay, so that's our strategy. Now let us see how. Now, one more thing that we observe is that the Riemann integral, see, the step functions are Lebesgue measurable. They are Lebesgue measurable functions. And their Riemann integral coincides with the Lebesgue integral. And in fact, you see that because of our assumption that f is a bounded function, see, these are bounded functions. These are Riemann integral. These are Lebesgue measurable functions because of the fact that the intervals are all Lebesgue measurable sets, and simply follows that these are measurable functions. And their in Riemann integral is essentially the Lebesgue integral. Okay. So now we assume that, okay, let's build the necessary ground. So f is bounded. on AB. That implies the functions phi n and psi n are uniformly bounded. Now you see, it's the right situation to apply the bounded convergence theorem. Let us just recall the bounded convergence theorem. Now we are working on the language of what you call the Lebesgue integration. Okay. So what you have is this. Okay. Let us recall bounded convergence. What does it say? It says the following. Suppose R and measurable and measure of E is y. Now these are the basic assumptions which are all satisfied in this situation. Okay. Suppose a sequence Fn is measurable. Is a measurable class of functions. Okay. Now, if Fn is uniformly bounded, this is what we said, that this phi n and psi n are uniformly bounded. Okay, that's the conclusion that we have made. Okay, see this conclusion. So F is bounded on AB implies are uniformly. Now this condition is already satisfied. And if the sequence Fn converges to F pointwise on E almost every time. So this is the part. If Fn converges to F pointwise on E almost everywhere, then what you have is this image tending to infinity. That means you can interchange the limiting process and the integration. So this is what we prove. See, essentially this is what we want to prove. Okay, because we have now the right scenario. That means we have phi n converges to F. I mean, if we can show that phi n converges to F, psi n converges to F, then instead of Fn you can put in phi n and psi n, and they all go to this, which in turn means that integral a to b psi n minus phi n, limit of this as n tends to infinity, is 0. This is exactly what we want to prove, that the function f is Riemann integrable. So let us prove this. Okay. Hence, okay. Now we shall apply the bounded convergence theorem to phi n and see, the only thing that remains to be shown, see, it can be applied provided phi n and psi n are uniformly bounded, which we have already inferred, okay? Which are uniformly. Now this we have already seen. Therefore, you know that, see, what you want to show is that this phi n and psi n at all points of continuity of f okay, all points of continuity of f converges to f. Okay, this is what we want to prove. So it is sufficient to prove that see, we have reduced the problem from working on every set, we see on the entire interval, to working it out only at the points of continuity of, that's sufficient. So it is sufficient to prove that point-wise, almost everywhere on AB. What we do is, we prove that at all points of continuity, okay, at all points of continuity, yeah, other than the partition point, which anyway form a set of measures 0. Okay. Therefore, what we are doing is that, so essentially, if you could prove that, okay. Phi n converges to F and F. This is what we want to prove. So at all points of continuity of F other than the partition points, we have this property, and from that you can make the inference. So let us prove this. So we are going to the last act. So let x naught be a point which is not a partition point, this x naught should not be confused with the the partition point I have marked there. It's not that. I mean, if you want, you can use another symbol for this. Okay, so let me use this. X tilde be a point which is not a partition point, and such that it's a point of continuity of F. Continuous at square. So we fix the point where we assume F is continuous. Now then we show that sorry. So both these sequences, one of course is an increasing sequence, the other one is a decreasing sequence. Phi n approximates from below and psi n approximates from above. This property that at those points phi n converges to F and psi n converges to F. So that we have the perfect situation where we can apply the bounded convergence theorem and come to the conclusion. So let epsilon positive. Let delta positive be such that fx naught minus epsilon by 2 plus epsilon by 2. X naught, x tilde, x tilde x tilde is less than. This is just the definition of continuity. Okay. Now this is what we want to prove actually. So let epsilon be chosen, let delta positive be such that this is true. Now we want to show that there exists an n such that for all n greater than n, this f tilde, fx lies, or phi nx and psi nx lie in this gap. Okay, that's what we want to prove. Okay, right. So choose n such that. So here we use the uniform boundedness. Gap of Pn is less than delta if n greater than or equal to n. And In, so we have started with an epsilon, we have got the corresponding delta using the continuity, and then using that delta we are now going to fix the n so that the gap of Pn is less than delta if n greater than n, and In is the open partition interval determined by Pn, which contains X tilde. So what you have is this, the length of In is certainly less than delta in that case, okay, right? Then In is contained in X tilde minus delta okay, right. So what happens? And that would imply, so you see, you are now going to apply the bounded convergence theorem. Okay. So what we have is this. This implies at x tilde, or what you have is this n psi n x tilde converges to f of x tilde. So at the points of continuity, see what you have is this. This is x tilde. This is the interval AB. Now you have x tilde minus delta. This is x tilde minus x tilde plus delta. And what we have is this, that because of this choice of capital N, such that the gap of this is less than delta, therefore you see that the interval In is contained in x tilde minus delta to x tilde plus delta. Or because because it's 2 delta distance that we have in this. Okay, so this is delta. This is delta. Look at the way in which delta has been chosen. Okay, then what is the conclusion that you have? So apply boundedness convergence theorem. Then this is true. Okay, and this, let us now apply the conclusion of this theorem. This implies integral of phi n converges to integral of f, and so also, and integral of a to b psi n converges to integral of f. This is the consequence of bounded convergence theorem. What does this mean? This implies integral of a to b phi n minus psi n, or sorry, because psi n is greater than or equal to phi n, that's why I am writing this. This is non-negative. This goes to 0, and that in turn implies that this is essentially the condition for the limit of this is essentially the lower integral, and the limit of this is essentially the upper integral. So this in turn tells you that the upper integral is equal to lower integral, and therefore this would mean that f is this in turn implies that f is Riemann. Okay, so that completes it. So we have characterized the class of functions which are Riemann. They should Riemann integrable if the points of discontinuity of f on AB is a set of measure 0. Thus, It is the same as saying that f is continuous almost everywhere. Of course, strictly speaking, the integration theory, we have completely cross-checked the whole thing, what it means for Riemann integrable functions. For Riemann integrable functions, it essentially, the Lebesgue integral is the same as the Riemann integral. So we have recast the whole thing in terms of what is called the language, in the language of measure. That means this should be a set of measure 0. Okay. So thank you very much. That completes the characterization. Now, what I intend to do from now on is to look at the relation between the integral and the derivative. You see, the fundamental theorem of calculus, how it manifests in the case of the Lebesgue integrable functions. And all this we have pointed out that it's something which we have to be watchful for. Okay? Right? Because we found that there are some shortcomings about the fundamental theorem of calculus to be applied for these Riemann integrable functions. Now we are going to ask what is the version of this in the context of Lebesgue integrable functions. So Lebesgue integrable functions form a very rich class of functions. In fact, you see that the Riemann integrable functions form a subclass of that. Okay? Right? So thank you very much. Let me conclude here. Okay, that's fine. Good. Systematic.